Acid rain is a major threat to Earth's environment. Every year, millions of tons of acid-forming gaseous pollutants are released into the air and make their way into our lakes and rivers. In some areas, the pH of lakes is dropping to critical levels. But the damage caused by acid rain is also evident in cities, in the country, on farms, and in our forests. Many buildings and monuments are being damaged by acid rain. It is also harming our soils by leaching out minerals, and this is especially true at high altitudes. In this program, you will learn what information you can obtain from a pH measurement, why pH is important to many living and non-living systems, and how pH measurements help scientists monitor the environment. You will also learn about some of the sources of this acid rain problem, as well as some of the solutions to this problem.
Now, we can learn a lot about the environment using a pH meter. Amadeo, what does a pH meter tell us?
Well, a pH meter would tell us if an aqueous solution is acidic, basic, or neutral.
Yeah, if the pH is less than 7, it's acidic. If it's greater than 7, it's basic. If it's exactly 7, it's neutral.
That's right. Now, the pH of lakes around the world vary quite a bit. Now, what if we had a body of water with a pH measurement of 4.5 compared to a body of water or a lake with a measurement of 5.8? How much more serious is that?
That would be a lot more serious, wouldn't it?
That's right, it could be. Now, we would like to know how much more acidic the lake at 4.5 would be. We want to know if we can learn anything from the pH measurements. Perhaps this could tell us what is happening to the lake, and we can compare this to normal rainwater.
I get the feeling we're going to get wet on this one, aren't we?
You are.
Now, we know already that water can have different pHs, right?
Mm-hmm.
So I'm guessing that rainwater would also have a different pH. So you would probably want us to go and collect some samples and then compare them.
That's right.
Well, where do we go and when do we start?
Well, I'd like you to start right away. And we're going to get an environmental chemist to help you with your sampling. And you're going to different sites to collect your samples. You can go ahead and grab the equipment behind you. And let's just have a quick review of sampling.
Okay, well, we don't use the same techniques everywhere, so we're consistent.
We'd also want to make sure that our sample was representative of the region that we were in.
Good.
If we were using equipment over again, we'd want to make sure we cleaned it really well to avoid contamination.
And we'd have to be very careful not to disturb the environment, right?
That's right. Now, let's have a look at the map. Amadeo, grab one end, Ryan the other. Okay, now, let's find some sampling sites. Where can you go?
Well, we could go to the creek over there.
That's right.
Or one of the bridges.
Good. Perhaps to the bog.
So, what are the pH ranges of various types of water?
Well, as you know already, pure rainwater would have a pH of about 5.6, and it can be lower, can go down to as low as 3.2. Ocean waters typically would be 7.3 to about 8.5. Freshwater systems like rivers and lakes would expect the pHs anywhere from 5.5 to 8.0. Groundwater, it can go down as low as 2.0 and up as high as 8.0 or sometimes higher. Okay, historically at this location we have found that the pH is between 7 and 7.5. So we know what kind of pH we're looking for when we test this sample.
So what would you do if the pH was outside the expected range?
Okay, if the pH is outside that expected range, then we would retest the sample. If it's still outside, we would then resample since we're here already. If it's still outside the range, we would check our pH meter and our pH electrode to make sure they are in order.
So how often do industries take samples from surrounding sites?
In Alberta, each industry that operates has a license to operate. And on that license, it will specify which chemical test parameters they have to do and how often they have to do it. So depending on what type of industry it is, some may have to do a pH once a day or more often. And others may not have to do it any more often than once a month. So it depends on the industry.
So, how do industry test methods compare to ours?
Well, the test method they're using for pH will be exactly the same as we're going to use. But if they were sampling for pH, they would sample where you sampled field, and then you'd also sample across the river at different distances, and they would also sample at different depths. And depending again on the situation, there are situations where they would have to sample upwind from the plant and downwind from the plant.
So, what other indicators in the environments besides pH could tell us that there was a problem with acid rain?
Okay, there are certain organisms that we call indicator organisms, so any change in numbers of their populations will indicate that there is a problem. We also look for changes in concentration of metals, increased concentrations of metals, and increased levels of sulfates and nitrates from the acidic deposition itself.
What's wrong?
Well, I think its pH meter's broken.
Why?
This is normal rainwater, and I'm getting a reading about 5.6. It shouldn't be that acidic, should it?
I don't think so. I don't think there's anything around here which could make it that acidic.
Well, hold on for a second. There's probably carbon dioxide and other gases that are dissolved in the air that would be produced by animals and used by plants for photosynthesis, right?
Yeah.
And couldn't that contribute to the acidity of the water? Because if you think about it, that's the way pop is made acidic. They bubble carbon dioxide gas right through it.
That's right. Okay. Well, why don't we test that?
Yeah, but where are we going to get a source of carbon dioxide?
We breathe out carbon dioxide.
That's right. Hold on a second.
That's pretty smart.
I think that should be long enough.
Okay, let's test the pH.
Hey, would you look at that?
Okay, that's perfect. That's exactly what we predicted.
Looks like you two have been very busy. What are you doing?
Well, as you can see, we've collected our samples from various locations. We've recorded the pH of each sample, and we've written it on the sample jars.
All right.
And on the map here, we recorded where we collected each sample from.
All right, then what?
Well, now our job is to calculate the concentration of hydronium ions in each of our solutions.
We're going to use the relationship hydronium ion concentration is equal to 10 to the negative pH.
Okay. Which sample are you going to start with?
Well, we'll start with this one, which has a pH of 5.60.
Okay. So can you show me using your computer?
Okay. Calculations would look like this. Concentration of hydronium ions is equal to 10 to the negative 5.60 is equal to 2.5118864 times 10 to the negative 6. So we round to two significant digits, we get 2.5 times 10 to the negative 6 moles per liter.
Okay. So that's the hydronium ion concentration for the first sample. Now, why is that sample so acidic?
Well, we collected it in a spruce forest. Maybe that has something to do with it. Are spruce trees acidic?
Yes, that would perhaps contribute to the acidity of that. That is not quite as acidic as some lakes that you can find actually in various parts of the world that have been affected by acid rain.
We also have to remember that the spruce forest, even though it was slightly acidic, still supports a wide variety of different living organisms.
Good. I think you're learning a lot from this activity. Continue on with your calculations.
Okay, well, this one has a pH of 6.80.
Okay.
The term acid rain is somewhat of a misnomer. A better name is acid deposition. That's because much of what we call acid rain actually enters our water supply in some other way. This could be in the form of snow, hail, fog, or even dust in the air. It doesn't matter if the pollution is from automobiles, gas plants, or other sources. If it lowers the pH of water, it's acid deposition.
Amadeo, what's on your mind?
Well, I was just wondering why some of the samples collected from the pond were slightly basic.
Well, actually, many shallow lakes are basic. It all depends on what's in the lake bed itself, whether it's calcium carbonate or some other basic material. See, what happens is that these bases can dissolve in the water and increase the pH, causing the basic lake water that we have. Let's suppose we have calcium carbonate in our lake bed. This can dissociate to produce calcium ions and carbonate ions. And then the carbonate ions can react with water to produce hydroxide ions. And hence we have the basic lake water. Okay. But most lakes that aren't polluted anyway have a slightly acidic pH. Now keep in mind that the pH scale is a continuum. And let's have a look at this sample of lake water here. We'll take a reading of the pH of this lake water, and look at that. Pretty close to 7.
Close to 7. Yeah.
All right, now under standard conditions, remember that 7, which is right around the middle of our pH scale, is the point at which the concentration of hydronium ions and hydroxide ions are equal. Okay? Now, I want you to use all of this information to assist you in this. I want you to determine the concentration of hydroxide ions and then the pOH of all of your samples of lake water that you have taken.
Now, when we're dealing with pOH, that would be dealing with the negative exponent of the concentration of hydroxide ions instead of hydronium ions, right?
Exactly right. Okay, and to review the calculations that you'll need to do, why don't you first of all determine the hydroxide concentration and the pOH of this sample of acidified water that I brought in with me.
Okay.
And the pH here, 3.80 to start with.
All right.
Go ahead.
Okay. Now, we'd start with our equation. Concentration of hydronium ions is equal to 10 to the negative pH. Then we'd take our equation for Kw and manipulate it so we could get our concentration of hydroxide ions.
Right, okay.
Now, we know that the pOH is equal to the negative log of the concentration of our hydroxide ions, and that's how we obtain our pOH value.
All right, sounds like you have it all planned out, so let's do it.
Okay, when we substitute in the pH of 3.80 into this equation, it gives us an answer of 1.5848931 times 10 to the negative 4 moles per liter, which is equal approximately to 1.6 times 10 to the negative 4 moles per liter. Then we take this value and we put it into the equation for the equilibrium constant of water.
Right.
And all we do is we divide the Kw, which is 1.00 times 10 to the negative 14 moles squared per liter squared, by the answer we got in the last equation.
Right.
And it gives us an answer of approximately 6.3 times 10 to the negative 11 moles per liter.
Okay, we're getting close now.
When we put that answer into the equation for pOH, negative log hydroxide ions concentration, we get an answer of approximately 10.20.
All right, good. Now, is there an easy way we can check our answer?
Well, we know that the pH plus the pOH is supposed to equal 14, and we can see that it does. So I'm guessing our answer is right.
Well, no guessing. It is right. Okay, guys, now that we've done our practice here, let's go ahead and do the real thing. What we want to know, once again, is the concentration of hydroxide ions and the pOH in all of these samples.
Okay.
All right.
Acid deposition comes from many sources, both natural and artificial. Examples of natural sources of acid rain include forest fires, volcanic eruptions, lightning, and even the bacterial action in soil when matter decomposes. Examples of human sources of acid rain include combustion of fossil fuels, smelting of ores, petroleum refining, and even sewage treatment. No matter what the source, 3 of the main gases that can result in acid deposition are carbon dioxide, nitrogen oxides, and sulfur oxides. It has been estimated that in the world each year, about 1 times 10 to the 15 kilograms of carbon dioxide are produced from natural sources, and over 2 times 10 to the 13 kilograms of carbon dioxide are produced by human activities. The carbon dioxide can react with moisture to produce carbonic acid. In addition, about 1.8 times 10 to the 11 kilograms of nitrogen oxides are produced from natural sources, while over 7 times 10 to the 10 kilograms are produced by humans. A common nitrogen oxide is nitrogen dioxide. Nitrogen dioxide can react with moisture and produce nitric and nitrous acids. Of the sulfur oxides produced, about 2 times 10 to the 10 kilograms comes from natural sources, while 2 times 10 to the 10 kilograms comes from human sources. A common sulfur oxide is sulfur dioxide. Sulfur dioxide can react with moisture to produce sulfurous acid. For millions of years, the Earth has been able to absorb most of the acid deposition produced. However, since the Industrial Revolution, more acid deposition is being produced than the Earth can absorb. These additional sources of acid deposition have stretched the Earth's ability to neutralize these acids and has resulted in our present acid deposition problem.
Are you finished comparing your results yet?
Yeah, we just finished confirming that pH plus pOH is always equal to 14.
So we can tell all sorts of neat stuff just from one pH measurement.
The information on the screen was part of the Science, Technology, and Society Open Response question. This is the background information. As the human population and the demands of society have expanded, a variety of energy sources have been developed to meet the needs of society and industry. All of the energy technologies affect the environment by either altering the geography or releasing substances. Now this is the question. Describe the composition of a substance that is currently being added to our environment. Explain the risks and benefits associated with this substance. Present an argument for how you think we should deal with this substance. The response to this question could take a redox, acid-base, or energetics perspective. Some suggested answers to this question can be found in the Learner's Guide for Program 40. This question is scored using holistic scoring guides, a major and a minor. The major student criterion is knowledge. Students answering the question must address all the key components of the question and correctly support their responses. The minor scoring criteria involve communication skills, which include those processes by which the information is exchanged through appropriate conventions, including words, sentences, and paragraphs, graphs and diagrams, mathematical and chemical formulas, mathematical and chemical equations, significant digits, units of measurements. All responses should reflect good organization and be presented in a clear, concise, and logical manner. So try the challenge question and check the Learner's Guide for examples of appropriate responses.
But what does all this mean?
Well, I'm not exactly sure. For example, let's say we have a pH of around 8 in one sample and 6 in the other. That means that we have an acidity, one is 100 times greater than the other. I know that, but if you think about it, the numbers are really small. That's only a change of 1/100,000th of a mole per liter of hydronium ions to 1/10,000,000th of a mole per liter of hydronium ions. I don't see how such a small change could make such a big difference.
Good question. Let's go ask the environmental chemists that helped collect these samples.
Hi, Mr. Warwick.
Hello.
Oh, hi.
We're back. We have to ask you a few more questions about our project.
Yes.
I'd like to know one thing. Why does a pH change of only one unit have such a drastic effect on the environment? Because if you think about it, let's say a change from pH of 6 to a change of pH of 5 would only be a change of 1/1,000,000th of a mole per liter to, say, 1/100,000th of a mole per liter. The numbers are very small.
Yes, most biochemical reactions and processes are very pH sensitive. So even a very small change in pH can adversely affect that biochemical reaction. And through time, that will eventually show up as some visible effect on the plant or the animal, on the organism.
I see.
Also, the organisms usually affected first are those at the very bottom of the food chain. So those are the ones we would monitor first.
Well, why are the pHs distributed the way they are on this map?
Okay, this map shows pH profile over North America over the past 40 years. And if you go back 40 years to the 1950s, you will see that there was a large area where the pH of water in lakes and rivers was 4.52. If you come right up to 1975-76, you'll see that there's quite a significant area where the pH is down to 4.1. And right up to 1986, you'll see that 4.1 line covers an even larger area. And this is because of the increased quantities of acidic emissions due to industrial activity.
Why is acid deposition not as big a problem on the prairies?
If you look at this map, you'll see that the major sources of SO2 emissions are here and a little bit here, not very much in the prairies. And the prevailing winds tend to move in a northeasterly direction. The second reason is, if you look at this map, this one shows the potential of soils and geology to reduce the acidity of atmospheric deposition. And the green area, right across the prairies, shows that this area has got a high potential to reduce the acidity of acid rain or acidic deposition.
I see. Well, thank you very much.
Thank you, Mr. Warwick.
You're welcome.
The Earth can only recycle so many pollutants. By burning fossil fuels and cutting down forests, humans are challenging the Earth's mechanisms for absorbing pollutants. Automobile exhaust is a major factor that contributes to acid deposition. Maybe it's time to think about public transport, carpooling, bicycling, or walking. Earlier, you learned that a change of one pH unit can mean the difference between life and death for many organisms. The reason is because the concentration changes by a factor of 10 for every change in one pH or pOH unit. And a change of 2 pH units means the concentration changes by 100 times. This would be much more obvious if hydronium ions or hydroxide ions were colored. Let me show you what I mean. If the food coloring in this beaker represented a hydronium ion concentration of 1 times 10 to the negative 6 moles per liter, its pH would be 6.0. This could be the pH of an unpolluted lake, we'll say. The pH changed from 6.0 to 5.0. This imaginary lake water would now show a hydronium ion concentration that is 10 times greater than the unpolluted lake. And if the pH decreased to 4.0, the lake water would be more polluted. The hydronium ion is now 100 times more concentrated than in the original water solution. If the pH decreased again to 3.0, the concentration of the hydronium ion was 0.001 moles per liter, which is 1,000 times more concentrated than in the original sample. This is analogous to what happens when lakes become acidified to a pH of 3.0 from 6.0. There is actually 1,000 times more acid in every liter of water, and that's a lot of acid, especially when you think of how many liters of water there are in a lake.
Acid rain may contain sulfuric acid, which can be formed from the emissions of sour gas wells, oil refineries, or power generating stations. Sulfuric acid forms when sulfur trioxide reacts with moisture. When acid rain falls, it results in billions of dollars of damage. The damage caused by acid deposition is not always as obvious as it is with this statue. Sometimes it isn't even noticeable for years. When acid rain in the form of sulfuric acid falls in a marble statue, a very slow reaction occurs. The calcium carbonate can react to produce calcium sulfate and carbonic acid. Since both of these compounds are to some extent soluble in water, the statue literally begins to dissolve. However, when acid rain in the form of sulfuric acid falls in cement, the cement does not dissolve. Instead, it weakens and eventually crumbles away. That's because a major ingredient in cement is calcium silicate. When sulfuric acid reacts with calcium silicate, water, silicon dioxide, and calcium sulfate may form. The calcium sulfate is only slightly soluble in water, but it will dissolve very slowly, leaving silicon dioxide behind. Another name for silicon dioxide is sand. The result? Flaking and weakened cement. But the problems don't stop there. Another major problem associated with acid deposition is leaching of metals from bedrock and soils. If heavy metals such as lead or mercury in the soil react, this can cause many health problems. When the metals in the soil are oxidized by an acid, they form cations and dissolve in the water. These ions can reach concentration levels dangerous to living organisms. Leaching also leads to problems if hazardous compounds are disposed of at landfills and later are dissolved by acidic rain. At high altitudes with very thin soil layers, acid deposition can leach out minerals which are essential for plant growth. Sometimes the effects of acid deposition are clearly visible, but more often they're out of sight, posing an invisible threat to the biosphere.
At the other end of the pH scale from acid deposition, we have cleaners like this. Some household cleaners can be just as basic as industrial cleaners, so great care must always be taken while using them. And because high pH can be just as hazardous to the environment as low pH, any unused household chemicals should be disposed of properly.
Now, Amadeo, you've learned a lot about acid rain. What about cleaning solutions?
Well, we know that the pH of the sodium hydroxide cleaner was 12. So from our logarithmic expression of Kw, we know that pH plus pOH equals 14, so pOH has to be 2. That would give us a hydroxide ion concentration of 1.0 times 10 to the negative 2 moles per liter, or 0.01 moles per liter, right? That would make for a pretty basic solution, don't you think?
Yes. Now let's have a look at a comparison. Here is the sodium hydroxide cleaner, pOH of 2. Here's water in comparison, pOH of 7. Now this is a difference of 5 pOH units. That means water is 10 to the 5th times less concentrated than the cleaner, or the sodium hydroxide cleaner is 10 to the 5th times more basic than water. Now if we compare the sodium hydroxide cleaner to typical rainwater, let's have a look. Notice that the rainwater is pOH of 8. That means that the cleaner is 1,000,000 times more basic than rainwater.
So that cleaner could be useful in neutralizing a lot of acidic lakes.
Well, we wouldn't use sodium hydroxide cleaner to help neutralize lakes, but we could use another base powdered limestone. Here's the reaction: calcium carbonate with water, then we form calcium hydroxide, which reacts with the acid in the lake. Now, this process is expensive, and it's not that effective in that all it does is it treats the symptom, not the cause of acid rain. So you have to keep on applying this process.
I see.
Now, we wouldn't use sodium hydroxide in this process because sodium hydroxide is dangerous to work with and it's very corrosive.
So, better to use cleaners sparingly and dispose of them at a hazardous waste depot.
That's right, especially the corrosive ones. Now, there's other cleaners that you could use that are gentler, such as baking soda and vinegar. Now, these do not have the extreme pH ranges some of the other cleaners do. And if you need more information, there's lots of books on the marketplace about using environmentally friendly alternatives.
Right. So, we have to use our cleaners more safely. We have to cut down on our fossil fuel consumption and try to develop some new technologies that will cut down on air pollution.
That's right.
In the industrial process used to make ammonia, CO2, a greenhouse gas, is produced as a byproduct. In producing the hydrogen, methane from natural gas is reacted with steam to form carbon monoxide and hydrogen. The carbon monoxide is then reacted with steam to form carbon dioxide and more hydrogen. The hydrogen we use to produce the ammonia. The CO2 has to be removed from the syngas, and we scrub it in this particular plant using hot potassium carbonate. The CO2 is then recovered from the hot potassium carbonate, and instead of venting it, we use it to make urea. Making urea from the CO2 minimizes our greenhouse gas emissions.
Rain. We need it to survive. Yet in some cases, rain brings harmful acid deposition. In this program, we learned what information can be obtained from a pH measurement. We saw that pH gives a measurement of the acidity or basicity of a solution, which can compare it to other solutions. We learned why measuring pH is an important way for scientists to monitor the environment. We discovered that most living organisms can only exist within a very narrow pH range, which is species-specific, from a maximum of 9 to a minimum of 5. Therefore, it is important that we try to minimize the effects of acid rain and maintain this delicate balance. And we looked at some of the sources of acid rain. We saw that acid deposition can come in many forms. Many are natural, and the Earth is able to absorb and recycle this deposition. However, when the human factor is added in, this balance may be upset. The main contributor is the combustion of fossil fuels. Acid deposition is not the only problem. Many other chemicals can affect the pH of our water supplies. We must learn to handle all of them properly to protect our planet.
Sometimes the effects of acid deposition are clearly visible.
Earlier, you learned that a change of 1 pH unit can mean the difference between life and death for many organisms. The reason is because the concentration changes by a factor of 10 for every change in 1 pH or pOH unit. And a change of 2 pH units means the concentration changes by 100 times.
Well, hold on a second. Now, these plants, they use carbon dioxide for photosynthesis. And there's animals all around here that are changing into carbon dioxide. No. That's right.